Hello again, guys. Welcome to lecture 3 of our lecture series, Chemistry for Engineers. Today we'll be looking at molecules, moles, and chemical equations. Our objective today will be understanding chemical reactions, elements, and their chemical properties. We will be learning how to balance chemical equations, also understanding the difference between a solute and a solvent, as well as electrolytes and non-electrolytes. Also understanding acid bases and to explain the basic concept of moles, interpret chemical equations as it relates to moles and molecules. A chemical reaction is basically when two or more molecules interact to form a product. In our first lecture, we actually looked at physical properties of elements, where we understood that physical properties include mass, density, volume, color, viscosity. Chemical properties describe the ability of a substance to interact to form new products. So in terms of balancing an equation, the universal law of conservation states that matter can neither be created or destroyed. If you start a chemical reaction with 10 atoms, you should end up with 10 atoms. So basically, in a chemical reaction, what you're seeing is a rearrangement of atoms. Chemical reactions do not actually change the building block, they simply transform into something else. So when balancing an equation, the number of atoms is the most important thing, because this means that the number of atoms on both sides has to be the same. The number of atoms on both sides has to be the same. A solute is a substance that dissolves in a solution. A solute is a substance that dissolves in a solution. A solvent is a substance that dissolves a solute. The solvent is usually liquid, but it can also be solid or gas. An electrolyte is a substance that conducts electric current as a result of dissociation into positive and negatively charged particles. We call those ions. A non-electrolyte is a compound that do not conduct electric current in an aqueous solution or in a molten state. An acid is a molecular ion that is capable of donating a proton. So a base is a chemical species that donate electrons, accept protons, or release hydroxide ions in aqueous solution. The concept of mole in chemistry looks at the amount of material that contains 6.022 times 10 to the 23 particles. 6.022 is also known as Avogadro's number. Here we observe an explosive chemical reaction, which means that two or more molecules are interacting to form a product, or reactants react to produce a product. One important characteristic of chemical reactions include evolution of a gas or formation of a gas. In this case, we have sodium sulfate and dilute hydrochloric acid reacting to give you sodium chloride, water, and sulfur dioxide gas. In this case, we have zinc and hydrogen sulfide producing zinc sulfide and hydrogen gas. Chemical reaction can also cause the formation of precipitate. So here we see the evolution of a gas. In the case of sodium sulfide and dilute hydrochloric acid, we can also have the formation of a precipitate. A precipitate is basically when a substance is converted to a solid form of a solution. In this case, we have copper sulfate in an aqueous solution, sodium hydroxide also in an aqueous solution, reacted to give you a blue precipitate of copper hydroxide. Here we see the solid state. Chemical reaction can also cause a color change, a temperature change, or a change in state. A color change is seen here, where we have a color change when citric acid is added to potassium permanganate. So potassium permanganate here is deep purple, and when the citric acid is added to the potassium permanganate, it basically becomes transparent. You also can have a temperature change. So in this case, you have barium hydroxide and ammonium chloride to form barium chloride, ammonia, and water. This is characterized by a fall in the temperature. You can also have a change in state, as we can see here. With combustion, you have a change of solid from solid to a liquid state to a gas state. The important thing to focus on today on the periodic table would be the atomic mass, because the atomic mass will assist us in calculating the molar mass of a given compound or the molar mass of a certain constituent constituent of atom. In our first two lectures, we looked at the group 1 element, group 2 elements as well. We also looked at the transition metals. These include group 3 to 12. We also did mention group 18 as well as 17, the halogens as well as the noble gases. So we will give a little attention to group 13, 14, 15, and 16 elements. The important things that we need to consider are the atomic number as well as the atomic mass. So for example, the atomic mass of hydrogen is 1.008. The atomic mass of lithium is 6.94. And let's retain a few, for example, when we get to calculating the molar mass. So for example, sodium, the atomic mass is 22.98. The atomic mass of aluminum is 26.98. Carbon is pretty common, 12.011. Nitrogen, 14.07. Silicon, 28.085, and so on. So you basically will have to refer to the periodic table for the atomic mass in terms of calculating the moles. So just a bit of refresher. For our first two lectures, we looked at the group 1 as well as group 2 elements. We also did discuss a little bit about the transition metals as well as the halogens in group 17 and the natural gases or the noble gases that are in group 18. We did not touch on the group 13 to 16 elements. So the group 13 elements include boron, aluminum, gallium, indium, thallium, nihonium. It's important to note that boron is the first metalloids in this group. Group 14 elements include carbon, silicon, germanium, tin, lead, and flerovium. So it's important to also highlight the metalloids in these groups, and remember that we mentioned that the metalloids are generally used as semiconductors because they conduct a little electricity but not a lot. The metalloids from group 14 include silicon, germanium. Group 15 elements include nitrogen, which we already know is a gas, phosphorus, arsenic, antimony, bismuth, and moscovium. So it's important to note again that arsenic, antimony are the metalloids from this group. Group 16 includes oxygen, which we already know is a gas, sulfur, selenium, tellurium, and boron and aluminum can make 3+ cations. The boron is the first metalloids from this group. It tends to form covalent bond. The rest, however, are metals: aluminum, gallium, indium, thallium, nihonium. Aluminum tends to form covalent bond as well, but it can also form ionic bond. Group 14 elements are known as the carbon group because carbon is basically situated at the top. These include carbon, silicon, germanium, tin, lead, and flerovium. The important thing about these carbon groups or the group 14 elements, they can form 4+ or 4-. So they can be 4+ cations or 4- anions, depending on what they're interacting with. So as we mentioned before, silicon, germanium are both metalloids that are able to form covalent bonds. Tin and lead are both metals. They also have the tendency to form covalent bonds. So group 15 is known as the nitrogen group because nitrogen sits at the top. It's also known as the pnictogen. So these include nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. So nitrogen and phosphorus are non-metals, while arsenic and antimony are metalloids. And of course, bismuth and moscovium are both metals. Nitrogen and phosphorus are capable of gaining 3+ cations to become nitride and phosphide, 3- anions, but they also have a tendency towards positive oxidation states in 3+, with +3 as well as +5. So it's important to note that nitrogen makes up 78% of the atmosphere. It's very abundant. This nitrogen is in the diatomic form. Phosphate you can find in ore, you can find it in China, Russia, Morocco, in the US. And finally, group 16 is known as the oxygen group. These include oxygen, sulfur, selenium, tellurium, polonium, as well as livermorium. It's important important to note that the oxygen group are also known as the chalcogen. So we already know that oxygen, sulfur, selenium, they are all nonmetals. The metalloids include tellurium, and polonium. Oxygen is the most abundant element in Earth's crust. It actually makes up 50% of the Earth's crust, 50% by mass. It makes up 89% of the ocean by mass. The atmosphere is 21% molecular oxygen. Sulfur you tend to find naturally in volcanoes or geothermal events. Sulfate can also be converted to solid sulfur by sulfur bacteria. We can also obtain sulfur from hydrogen sulfide in natural gas. And it can also be reacted with oxygen to produce sulfur dioxide and water. So another important focus or properties that we need to focus on when looking at the periodic table are what we call electrolytes. The electrolytes we said are good conductors of electricity and can include group 1 metals, for example, sodium, potassium. We also have the non-electrolytes. There are certain metals that will conform to the solubility rule, and the group 1 metals tend to be highly soluble. Insoluble, silver, lead, and mercury. Silver, lead, mercury. Soluble, we also have chlorine, bromine, iodine as well. In terms of chemical reaction, the most fundamental requirement of an explosive reaction is that it must release large amount of energy. This release of energy is what might be described as force of explosion. The most fundamental requirement of an explosive reaction is that it must release large amount of energy. The release of energy is responsible for what might be described as the force of explosion. With the release of energy, complex compounds decomposes to form a collection of smaller molecules. This means that power equal energy per unit time. Explosives can be solid, can be liquid. Traditionally, explosives used to be liquid, but that was dangerous. The invention of dynamite provided a powerful explosive in solid form. The actual explosive in dynamite is nitroglycerin. Nitroglycerin is a liquid under ordinary conditions, so its use as commercial explosive was extremely hazardous. The molecular formula for nitroglycerin is C3H5N3O9, and we have the representation here. So we have 3 carbon, 5 hydrogen. This is 2, 2, 1, 3 nitrogen, and 9 oxygen molecule. 3, 2, 4, 6, 9. When a chemical reaction transforms a solid explosives into a large number of gaseous molecules, the gases will initially occupy the volumes similar to that of the solid. Explosives that are solid tend to transform in a gaseous state, but in the solid form, it basically occupies the volume similar to that of the solid. Gases have much lower densities than solid, so the gaseous products tend to expand rapidly to reach their normal density, which is why explosion from solid to gas tend to occur rapidly, because gases tend to have lower densities. So upon release, they rapidly escape to reach their natural density. In terms of explosions, there's the macroscopic, the microscopic, and the symbolic perspective. So here we can see a color change. Here we can see the chemical property or microscopic properties of explosives, and these can also be converted to symbolic representation of explosive. The molecular formula for RDX, or Research Department Explosive or Royal Demolition Explosion, is C3H6N6O6. 3 carbon should be represented here, 6 hydrogen, and remember we say that the carbon and hydrogen are not represented. 6 hydrogen, 6 nitrogen, 6 oxygen. So it's important to note that these are very explosive compounds. P10, for example, chemical formula, molecular formula is C5H8N4O12. P10 is pentaerythritol. Chemical formula or molecular formula is C5H8N4O12. C5H8N4O12. 2, 4, 6, 6, 8, 10, 12. Trinitrotoluene is also highly explosive. The molecular formula is C7H5N3O6. C7H5N3O6. This is nitroglycerin, which we touched a bit on. So it's important to note that these are highly explosive compounds that can produce important chemical reactions. So in terms of a chemical explosion, the molecules are tightly packed in solid explosive. With detonation, you have the formation of smaller gas molecules in product that are initially highly compressed. So you have the formation of smaller gas molecules, and with the gas molecules will continue to expand rapidly to reach their normal density. So when looking at chemical equations are designed to represent transformation of one or more chemical species into a new substance. Each chemical equation has two sides. You have a right side and a left side and a right side. The left side has the reactant, the right side has the product. Here we have methane interacting with oxygen. This will produce carbon dioxide and water. Methane with oxygen, with exposure to heat, you have the production of carbon dioxide and water. So the important thing about the chemical equation is that this side would be the reactant, which is the left side. This side would be the product. So the product would be carbon dioxide and water molecules. And the important thing is both sides have to be balanced, meaning that both sides will have to have the same number of atoms, because the law of conservation states that the atoms cannot be created nor destroyed. They basically just change into a different state. So here we can see where methane molecule plus oxygen molecule on exposure to heat produce carbon dioxide and water molecule, which basically means that there's a rearrangement of the atoms. On the side of the reactant, you have one carbon atom, four hydrogen atom, four oxygen atom, and it basically gives a product of one carbon, four hydrogen, and four oxygen. So there is essentially a reconfiguration of atom, but they remain the same. The original materials are called the reactants, and they appear on the left side of the equation. The compounds that are formed from the reaction are called products and appear on the right-hand side of the equation. The arrow is used to represent the change that occurred during the reaction. So here we have hydrogen and oxygen to produce water. The physical states of chemical compounds are given in the chemical equation. So there are three different states. The physical states can be solid, can be liquid, or it can be a gas. The symbols are written as S or L or G. If it's dissolved in water, it's in an aqueous solution. So it's basically designated AQ. So for example, solid potassium, which is designated S here, plus water, which is liquid, gives you hydrogen gas, which is H2 gas, and potassium hydroxide dissolved in water, which results in an aqueous solution. So here we see 2 hydrogen gas plus oxygen gas gives you 2 water molecule in the form of gas. Sodium plus chloride gives you sodium chloride. Ion in the form of solid plus water molecules in the form of gas gives you ferric oxide and hydrogen molecules as well. Zinc plus hydrochloric acid gives you zinc chloride plus hydrogen gas. So here we also have the representation of physical states in chemical equation, where we have 2 hydrogen molecule in the form of gas, 2 oxygen in the form of gas gives you 2 H2O. And as you can see, this is a balanced equation. A balloon filled with a mixture of hydrogen and oxygen explodes in a classroom demonstration. The gas mixture in the balloon is stable until ignited by the flame from a candle. Once ignited, the balloon explodes in the ball of flame as the reaction takes place. The occupying microscope scale illustration shows the molecular species present before and after the reaction. So the reactants are here and the products are here. So the hydrogen and oxygen gas forms a stable form of H2O gas. One characteristic of this reaction is that it will only occur at high temperature. So the important thing is that this reaction will will only occur at high temperature. The mixture of hydrogen and oxygen is stable unless ignited. Generally, this is done by placing a symbol over the arrow. So the symbol of heat in Greek is delta. So they usually put a symbol above the arrow, which indicates that in order for these reactants, the hydrogen and oxygen reactants, to form this product, high temperature is required or heat is required. And sometimes there's also light energy that is required as well. So in this case, a photochemical reaction is a reaction where there is light. So light is necessary for the reactant to form the product. One that is initiated by light and is designated with this symbol here, HN. The first equation is a more complete description of reaction between hydrogen and oxygen. In the second equation, light energy is used to initiate the reaction of hydrogen with chloride, producing hydrogen chloride. Such a light-induced process is called photochemical reaction. So here we see this is the first reaction that requires heat. This is the second reaction that requires light. As you can see, hydrogen and chloride gas basically exposed to light will give you hydrogen chloride gas. And again, one of the most fundamental law of nature is the law of conservation of matter. If we specifically exclude nuclear reaction from our consideration, this law can be phrased more specifically. Atoms of one element are neither created nor destroyed in a chemical reaction. A chemical reaction simply rearranges the atom present into new compounds. And as we can see, methane and oxygen gives you carbon dioxide and water. And if this is a balanced equation. Methane, CH4 plus oxygen reacts to produce carbon dioxide and water. On both sides, you have one carbon. The side of the reactant or the left side, you have one carbon here, four hydrogen here. 2 times 2 is 4 hydrogen, 4 oxygen. This is 2 oxygen, 2 2's 4 oxygen, as well as 4 oxygen here as well. And this represents a balanced equation. The chemical reaction for the burning of methane is, as we demonstrated before, in oxygen illustrates the concept of atom balance from chemical equation. The equation is shown first in the symbolic form, with each compound represented by its chemical formula. The individual molecules are pictured in the center row and then are broken down into the constituent atoms. The number of atoms of the element is the same on the left and on the right. So the important thing about balancing the equation is that in the end, the reactants and the product will all have the same amount of atoms. Here we have 1 carbon, 4 hydrogen, 4 oxygen, 1 carbon, 4 hydrogen, 4 oxygen. Methane plus oxygen reacts to give you carbon dioxide and water as a product. But in the end, even though the atoms or the configuration of the atoms will change to form a different compound, you end up with the same number of atoms, because the law of conservation states that matter cannot be created nor destroyed. So the important thing to understand with balancing equation is the stoichiometric coefficient. Stoichiometry refers to the various quantitative relationship between the amount of reactants and the product in a chemical reaction. So the numbers used to balance a chemical equation are called the stoichiometric coefficient. So the numbers that you put here, and you guys will have to learn how to balance equations, and we'll get to that in a bit more detail in a practical sense. So the numbers that are inserted here to balance the equation on the side of the reactant and the product is called the stoichiometric coefficient. So here we have propane, C3H8. The problem notes that propane burns or explodes by combining with oxygen. The reactants are therefore C3H8 and O2. The products are carbon dioxide and water. Here we have propane combining with oxygen to give you carbon dioxide as a product and water. So the mass and reactant of product should be equal after the chemical reaction. So we have to learn how to balance these equations. So this is the balanced equation. Let's see what was done here. So we have, this is the actual equation. If you omit the 4, that was inserted. Methane plus chloride reacts to form calcium chloride and hydrochloric acid. On this side, you have 1 carbon, 4 hydrogen, 1 carbon, 4 hydrogen, 2 chloride, 1 carbon, 1 hydrogen, 5 chloride. With the insertion of 4, this basically gives you 8 chloride. 4 times 1, 4, plus this is already 4, so that would give you 8 chloride here. The hydrogen would be 4 and the chloride remains 1. And in this case, you insert 4 here, so you also have 4 times 2, 8, so you end up with 8 chloride as well. So in this case, you have 4 hydrogen here, 4 hydrogen here, and you end up with a balanced equation. So you have 1 carbon, 4 hydrogen, 8 chloride, 2 times 4, 8. That gives you 1 chloride, 8 chloride, 4 hydrogen, 8 chloride, 4 plus 4. All right, so here we will be balancing this equation. So we basically have xenon and fluoride. And this is the product. So on this side, we have 1 xenon. On the side of the product, we have also 1 xenon. We have 2 fluoride. On the side of the product, we have 6 fluoride. So here you can see this is not a balanced equation. So how do we get a balanced equation? How do we get to have 6 fluoride on both sides? So what we can do, we can insert 3 and we end up with 6 fluoride, and we basically have a balanced equation. Here's another example. We have silver plus hydrogen sulfide. That basically gives you this product, Ag2SH2. So on this side, we have 1 silver. On the side of the reactant, on the side of the product, we have 2. We have 2 hydrogen, 2 hydrogen here as well on the right side. One sulfur on this side, as well as 1 on this side. So here we have an equation that's not balanced. We have 1 silver on the left side and basically 2 on the right side. So how do we balance this equation? We basically had 2. And we end up with a balanced equation. So here we have potassium hydroxide plus carbon dioxide. That gives you potassium carbonate, KCO3, plus H2. Oh, so on this side, we have 1 potassium, 2 on this side, 1, 2. So we basically have 3 oxygen on that side. So this should be actually 4 oxygen on this side, 1 hydrogen on the left, 2 on the right, 1 carbon, as well as 1 carbon. So how do we get a balanced equation? So here we basically should have 3, so forgive me. So we can balance this equation by inserting 2 here, and we end up with 4 oxygen instead of 3. Remember, this is supposed to be 3. End up with 2 hydrogen And voila, we end up with a balanced equation. So here we have sodium plus chloride. That basically gives you sodium chloride. So on this side, we have 1 sodium. On this side, we have 2 chloride. This side, we have 1 sodium, as well as 1 chloride. So how do we balance the equation? We basically need 2 chloride on the side of the reactant, right? So if you insert 2, we have a balanced equation. So because we have 2 and 1 on that side, we basically have to balance the side of the product. So here we have ferrous oxide plus carbon, which basically gives you FeCO2. So on this side, we have 1 iron. We also have 1 on this side. 1 oxygen. 2 oxygen on this side. 1 carbon. As well as 1 carbon on this side. So we have 2 oxygens. So if we insert 2 on this side, we basically end up with 2 oxygen on the side of the reactant and 2 iron. And this is basically how we balance this equation. For a chemical reaction to occur, the reactants involved must be able to come into contact with one another in the gas or solid phase. The molecules that make up the reactants move readily, allowing this contact to occur. Reactions that occur in water are said to take place in aqueous solution. Although water accounts for vast majority of all molecules in an aqueous solution, it's neither a reactant nor a product in many aqueous reactions. Water simply serves as the medium in which reaction occur. The entire liquid is called a solution, meaning that it is a homogeneous mixture of 2 or more substances. So the solution is the water, which is a homogeneous mixture of 2 or more substances, and the solute is the substance that will dissolve in the solution, and the solvent is the liquid that the solute dissolves in. So in terms of solution, solvent, and solute, in any solution, the component present in much greater amount is called the solvent. The solvent is a component present in greater amount. In an aqueous solution, water is the solvent. Minor compounds of the solution are called solute. So the minor stuff, the minor compounds are called the solute. The solvent is what is present in greater amount. So the solvent is what is present in greater amount. The minor component is the solute, and the key feature of a solution is that the solutes dissolve in a solvent. So the minor, which is the solute, dissolve in the major, which is the solvent. Not all solutions are even liquids. The same idea can be applied to homogeneous mixture of gases or solids. Air is a good example of gaseous solution, and alloys like brass can be described as solid solution. So you have different types of solution. Water can be a solution, metal can be a solution. The salt in the water is the solute. Gas also can be a solution. Solubility looks at the ability of the compound to dissolve in the solution. Compounds that dissolve readily in water is said to be soluble. Those that do not dissolve in water are said to be insoluble. So here you can see, for example, salt would be soluble. Oil, for example, would be insoluble. Sugar, in this case, would be insoluble. Salt would be soluble. Sand would be insoluble, which means that it does not have the ability to dissolve in a solution. One final observation to make about solution is that many ionic compounds will dissociate into individual ions when they dissolve into water. Thus, salt solution above actually contains sodium chloride ion and not sodium chloride molecule. So ionic compounds, when you put them in the solution, they have the ability to dissociate. Sodium and chloride will no longer be sodium chloride molecules, but would be sodium chloride ion. They exist as separate entities. Too much solute in a solvent will establish a saturated solution. So here again is just emphasizing the difference between solubility of a solute that can dissolve in a given amount of solvent. So you can have an unsaturated solution which contains less than the maximum amount of solute, can dissolve more solute. Saturated solution contains the maximum amount of solute. So you can have an unsaturated solution or a saturated solution. An unsaturated solution contains less than the maximum amount of solute. So basically it can dissolve more solute, and the saturated solution contains the maximum amount of solute that can dissolve. So you basically will have undissolved solute at the bottom of the container in this case. So this is an unsaturated solution here, and this is a saturated solution. So you basically will have undissolved particles or compounds at the bottom of the container. There are different solubility rules which you guys should know. The group 1 elements, as previously mentioned, group 1 cations tend to be soluble, which means that they have the ability to dissolve in a solution. For example, lithium, sodium, potassium, rubidium, cesium, ammonium tends to be highly soluble. The nitrates and nitrites tend to be soluble. Chloride, bromide, iodines also tend to be soluble, as we mentioned before. Fluorides as well as sulfate. The exceptions, insoluble, are silver, mercury, lead, silver chloride, mercury chloride, lead chloride, silver bromide, mercury bromide, lead bromide, silver iodine, mercury iodine. Insoluble are also magnesium fluoride, calcium fluoride, strontium fluoride, barium fluoride, lead fluoride. Insoluble, barium sulfide, lead sulfide, mercury sulfide. Usually insoluble are the phosphates, it's important to note, and the carbonate, the hydroxide, and the sulfides. However, you have some exception. You have ammonium phosphate, trisodium phosphate, tripotassium phosphate. In terms of the carbonate, and these are the exceptions: ammonium carbonate, sodium carbonate, potassium carbonate. In terms of the hydroxide, the exceptions are soluble lithium hydroxide, sodium hydroxide, potassium hydroxide, barium hydroxide. And the exception of the sulfides are potassium sulfide, sodium sulfide, magnesium sulfide, calcium sulfide. The phosphate, carbonate, hydroxide, sulfides are usually insoluble. So we looked at a saturated solution before, and we know that the concentration at which a given solution will become saturated depends on the identity of the solute. So it is useful to have a quantitative measure of solubility. The units used to report this number can vary, but one common choice is a molar mass of solutes per 100 gram of solvent. For example, the solubility of table salt in water at room temperature is 35.7 grams sodium chloride per 100 gram of H2O per 100 grams of water. So we looked a little bit on the electrolytes at the introduction. Availability of free moving charges allow these solutions to conduct electricity. Any substance that dissolves in water to produce produce an aqueous solution that conducts electricity is called an electrolyte. And we already mentioned the few electrolytes from the group 1 element. Substances whose solution do not conduct electricity are called non-electrolytes. The electrolytes are any substance that dissolve in water to produce an aqueous solution that conducts electricity is called an electrolyte. Electrolytes can be strong, electrolytes can be weak. Strong electrolytes are strong acids, strong bases. Weak electrolytes are weak acid and weak bases. Here we have the representation of electrolyte here. So if you have extensive current flow, this is a strong electrolyte. You have some current flow, this is basically a weak electrolyte. No current flow, it's a non-electrolyte, which means that it does not produce electricity in an aqueous solution. We can divide electrolytes further into two groups, as we mentioned before. Strong electrolyte dissociate completely so that only individual ions are present in the solution with virtually no intact molecules. So as we mentioned before, you can put sodium chloride in an aqueous solution. The sodium chloride molecule will dissociate into sodium chloride ions, and this will basically form the basis of the electrical excitation. In contrast, weak electrolytes only dissociate partially. Their solution contains both intact molecules and individual ions in measurable quantity. Examples of strong electrolytes include sodium hydroxide, sodium chloride, hydrochloric acid. Example of weak electrolytes include water, acetic acid, and ammonia. Non-electrolytes include sugar, alcohol, oil, and as we've seen before, these do not dissolve or dissociate in the solution. So therefore, they will not be able to conduct electricity. The photo shows a classroom demonstration in which a pair of copper rods is dipped in different solution. If the solution conducts electricity, a circuit is closed and the light bulb lights. Ordinary sugar, C12H22O11, is a non-electrolyte, so a solution of sugar dissolved in water does not conduct electricity. So if you put some sugar in a water and you put the copper rod that is supposed to be a conduit to conduct the electricity, there will be no indication of electricity because sugar is a non-electrolyte. A solution of sugar dissolved in water does not conduct electricity. This image here basically shows that a solution of sugar molecule in water does not conduct electricity. B is basically showing acetic acid CH3COOH, which is a weak electrolyte. An acetic acid solution contains low concentration of ions and conduct electricity well enough to light the bulb dimly. Potassium chromate K2CrO4 is a strong electrolyte. Potassium chromate solution contains higher concentration of ions and conduct electricity well enough to light the bulb brightly. The illustration accompanying each photo emphasizes the solute species in each solution. So here we can see sugar, a non-electrolyte, acetic acid, a weak electrolyte, potassium ion, a strong electrolyte here. When a covalently bonded material such as a sugar dissolve in water, the molecules remain intact. C6H12O6 is solid. When it reacts with water in an aqueous solution, it basically remains the same. So the chemical composition of sugar is basically the same in water. And this is very important to remember, right? By contrast, when an ionic solid dissolves in water, it breaks into constituent ions. This is called a dissociation reaction. The dissolving of sodium chloride above is a common example of the process. So you guys just need to remember the difference. What will dissociate in water or not? What is a weak electrolyte? What is a non-electrolyte? What is a strong electrolyte? And a dissociation reaction. So here we see that sodium chloride as a solid is dissociated into sodium ion in the aqueous solution and sodium cations and chloride anion in aqueous solution. So this is basically representing the dissociation reaction. Ammonium nitrate is a precursor to many important explosives and also has considerable explosive potential itself. So we look at chemical reaction in the form of producing electricity. Now we're looking at chemical reaction in the form of producing explosives. So because ammonium nitrate is also widely used as fertilizer, it is readily available for purchase. An unfortunate result of this availability is that it has been used in bombings, including the 1955 attack on the Mohara Federal Building in Oklahoma City. So basically, ammonia plus nitric acid gives you ammonium nitrate. This includes 1 nitrogen plus 3 hydrogen with nitric acid to form ammonium nitride. In the commercial preparation of ammonium nitride, pure ammonia in the gas phase is combined with concentrated aqueous nitric acid, HNO3. This produces a highly concentrated aqueous solution of ammonium nitrate, which is then dried and formed in small pellets called prills. The molecular equation shows that the complete formula of each compound involved, both intact and dissociated compound, are shown, followed by an aqueous to designate an aqueous solution when appropriate. So this is basically just showing the ammonia with nitric oxide to produce ammonium nitrate. Frequently, the compounds involved in aqueous chemistry are ionic. As is true with both nitric acid and ammonium nitrate, these ionic compounds dissociate when they dissolve in water, so the actual solution does not contain intact molecules of these compounds. So basically, the focus of chemical reactions is centered around solutions in solvent or an aqueous solution, or the solution being aqueous. The dissociation is emphasized if we write the total ion equation rather than the molecular equation. This form emphasizes that what is actually present in reacting mixture by writing dissociated compounds as separated ions in solution. The total ionic equation of, for example, reaction form above is thus: ammonium nitric oxide plus ammonium gives you ammonium nitrate. So the net ionic equation and complete ionic equation. So the difference is that there are spectator ions in the molecular balance or molecular equation as well as a complete equation, but the net ionic equation basically constitute the compounds that form the natural reactants. Ions that are uninvolved in chemistry are referred as spectator ions. In many instances, we are not particularly concerned with the spectator ion and need not include them in chemical equation. When spectator ions are left out, the result is a net ionic equation. So here we can see the net ionic equation is basically when you leave out the spectator ions. The spectator ions do not necessarily contribute to the reaction itself. These are just byproduct of the combination of the reaction. Hydrogen ion is rather special because it's present in all aqueous solutions. So I guess hydrogen ion can be a common spectator ion. Aqueous solution of acid. Strictly speaking, an hydrogen ion would be nothing more than a proton. Nothing more than a proton, but we will see in more details later, such a bare proton in aqueous solution actually be tightly surrounded by a water molecule. Thus, the ion is frequently written as HO to remind. So spectator ions are present on both the reactant and the product side of a chemical equation. So how do you identify a spectator ion? In this case, as you can see, the spectator ion would be here. Two especially important categories of aqueous solution are acid and bases. For our present purpose, we will define acid. So acid can be defined as any substances that dissolve in water to produce hydrogen ion or H3O ions or hydronium ions. Base as any substance that dissolve in water to produce hydroxyl ions or hydroxide ions. So here we have acids. Acid can be strong, acid can be weak. So here you have acids, any substance that dissolve to produce hydrogen ion, and we have 3 of them here. And bases, will produce hydroxyl group. So here we have the hydroxyl group. Like other solutes, acid and bases can be either strong or weak electrolytes. Strong acids or bases dissociate completely in water so that the resulting solution contains essentially no intact solute molecule. We can write the following equation of the dissociation of hydrochloric acid and sodium hydroxide. Strong acid, hydrochloric acid gas plus water result in hydronium in aqueous solution and chloride. So this is basically a strong acid, hydronium and chloride ions. Strong base will produce, as we mentioned before, hydroxyl group. Sodium hydroxide that produces sodium and an hydroxyl group. So acids are going to have H, hydrogen ion, in front of them, while the bases will have the hydroxide or hydroxyl group. So example of strong acids include HCl, hydrochloric acid, HNO3, nitric acid, H2SO4, sulfuric acid, HClO4, perchloric acid, HBr, hydrobromic acid, HI, hydriodic acid. Weak acids include phosphoric acid, hydrofluoric acid, acetic acid, hydrocyanic acid. Strong bases include LiOH, lithium hydroxide, sodium hydroxide, KOH, potassium hydroxide, CaOH, calcium hydroxide, barium hydroxide, strontium hydroxide. Weak bases include ammonia. The particular number that chemists choose to count by is in mole. This is known as the Avogadro's number. 1 mole is defined as the number of atoms in exactly 12 grams of 12 carbon. This number is also reflected as Avogadro's number, and it is a value at 6.022 times 10 to the 23. 1 mole of atom is 6.02 times 10 to the 23. When chemists want to count molecules, they count by mole so that the resulting number will be easier to work with. Mass of a single atom using Avogadro's number. How do you know a mass of a single atom using Avogadro's number? The mass of a single atom, you basically use the atomic mass of the element divided by the Avogadro's number. For example, the mass of silver atom would be 107.89 grams per mole divided by 6.02 times 10 to the 23. So therefore, the mass of silver atom would be 1.792 times 10 to the minus 22. So the mass of a single atom is equivalent to the atomic mass. So you're basically dividing the atomic mass of the element. And if you look at the periodic table, you would know the atomic mass of the element. You divide this by Avogadro's number, which is 6.022 times 10 to the 23 per mole. And that basically gives you the mass of the relative atom. For example, hydrogen consists of an atomic mass of 1. Helium consists of an atomic mass of 4. That would be 1 divided by 6. 4 divided by 6 times 10 to the 23. How do we determine molar mass? Our definition of mole said that the mole of carbon-12 has a mass of exactly 12 grams. Earlier we said that an atom of carbon-12 has a mass of exactly 12 atomic mass units. This is not merely a coincidence, but rather a very deliberate decision. Once we've decided that the atomic mass and the gram independently, Avogadro's number is fixed and the number of atomic mass is 1 gram. Here we show how the mass of an atom can be converted into grams or mole. So the mass of 6.02 times 10 to the 23 atom of an element is the molar mass of that element. Its value is gram per mole, is given in most periodic tables. The molar mass of silicon, for example, is greater than that of carbon because an atom of silicon is heavier than an atom of carbon. 1 mole sample of various elements are shown left to right. 1 mole of bromine, 1 mole of bromine, aluminum, mercury, copper, sulfur, zinc, iron, and we will end today by calculating the molar mass of sulfur dioxide, isopropyl alcohol or isopropanol, sulfur dioxide, which is SO2, isopropanol, calcium nitrate, and ammonium phosphate. So here we'll have to find the atomic mass of sulfur. Here we'll find the atomic mass of sulfur is 32. Here we'll find the atomic mass of oxygen is 15 or 16.00. Carbon 12, hydrogen 1.008, oxygen again, calcium which is 40, nitrogen 14, oxygen again here, nitrogen. So here we find nitrogen, hydrogen, phosphate or phosphorus, and oxygen. So we basically will have to find the atomic mass of sulfur. So we have 1 sulfur, 2 oxygen. So the atomic mass of sulfur is 32.07. The atomic mass of oxygen, 16.00. So to calculate the molar mass, that would be 1 times 32 plus 32.07 plus 2 times 16 is the molar mass of oxygen. This basically gives us 64.07 grams per mole. And this means that 1 mole of sulfur dioxide weighs 64.7 grams. Let's try isopropanol, C3H8. Oh, so we have 3 carbon, 8 hydrogen, 1 oxygen. So the atomic mass of carbon is 12. The atomic mass of hydrogen is 1.01. Oxygen, we already know, is 16. So this will be 3 times 12 plus 8 times 1.01 plus 1.16. This gives us 60.11 grams per mole. Which means that 1 mole of C3H8O weighs 60.11 grams. All right, let's try another one, calcium nitrate. So we have Ca, NO3. So we have a parentheses, which is a bracket, NO3 bracket times 2. So that's basically what that means. So you'll have to find the atomic mass of calcium, which is 40.08. So we have 1 calcium. We have 2 times, we have 2 nitrogen. We have 3 times 2, 3 to 6. So calcium is 40.08. Nitrogen 14. Oxygen, we already know, is 16. So this will be 1 times 40.08 plus 14 plus 2 times 14.01 plus 6 times 16. This gives us 164.10 per mole, which means that 1 mole of calcium nitrate weighs 164 grams. Right, let's try another one, the last one, ammonium phosphate. So we have NH4. Let's just keep this in red. NH4. And we also have a parentheses here. 3 PO4. So we have 1 nitrogen times 3. 1 hydrogen times 3, 4 is 12. 3 times 4 is 12. We have 1 phosphorus and 4 oxygen. So the atomic mass of nitrogen is 14.0. 1. Hydrogen, 1.01. Phosphorus, 30.97. Oxygen, we already know, is 16. So 3 times 14.01 plus 12 times 1.01 plus 1 times 30.9 plus 4 times 16. This gives us 149.12 grams per mole, which means that 1 mole of NH4 3PO4 or ammonium phosphate weighs 149.12 grams. This marks the end of our lecture today. So the important things to focus on today for today's lecture is balancing the equations, calculating the molar mass, ensure that you guys understand the solubility rules, what constitute a strong acid, strong base, what we considered electrolytes and non-electrolytes. Those are, I would say, would be the important focus of this lecture. So that's it for today, guys. Hopefully this has been informative. Feel free to ask your questions, and we'll see you for the next lecture.